Bismillah Rahman Rahim. In this session, we will discuss exam style questions on electrical quantities topic from O-level physics or IGCSE physics. So, explain in terms of electron movements what happens when a piece of cellulose acetate becomes positively charged by being rubbed with a cloth. The production of charge by rubbing can be explained by supposing that friction causes electron to be transferred from one material to the other. So, if cellulose acetate becomes positive charge, means some of the electrons has transferred to the cloth. So, for example, when cellulose acetate is rubbed with a cloth, electron go from the acetate to the cloth, leaving the acetate short of electron that is positively charged. That cloth now has more electron than proton and becomes negatively charged. So the cloth becomes negatively charged as the cellulose acetate is positively charged. Note that it is only electron which moves. The proton remains fixed in the nucleus. So this is the way that some materials becomes positively charged and the others negatively charged. So this is the way that movement of electrons causes positively charged some of the material due to the friction. It all happens due to the friction because this is all insulating materials. So part B, two positively electrostatic charge are brought closer together. Will they be repelled or attracted to each other? They always, like charges always repelled, unlike charges always attract. In the part B, a positive and a negative electric charges are brought closer to each other. Will they be attracted or repelled from each other? Attracted, because they are opposite charges, unlike charges. How many type of electric charges are there? Two, a positive or a negative charge. So describe an experiment to distinguish between an electrical conductor and insulator. For this purpose, a gold leaf electroscope type instrument is there. It could be used to perform electrical conduction and insulation. So insulators and conductors touch the cap of the electroscope with a different things such as a piece of paper, wire, your finger, thumb and cotton kerchief. So this is all the procedure that is written there. So we can learn it from the book. In part B, identify two good electrical conductors. All metals and carbons are good conductors. So all metals and carbons are good conductors. And electrical insulators, good insulators include plastic such as polythene, cellulose acetate. These are insulators, perpex and nylon. Now the part D, explain the difference between the electrical conductor and insulator in terms of electron. In terms of electron, we will now describe it. In an insulator, all electrons are bound firmly to their atoms. Insulators contains strong, firmly bound electrons within the atom. In a conductor, some electrons can move freely from atoms to atom. However, in a conductors, free electrons are available. In insulator, usually free electrons are not available. So an insulator can be charged by rubbing, causing the charge produced cannot move from where the rubbing occurs. That is, the electric charge is static. So these kind of charges, if something happens, may produce some static charge. A conductor will become charged only if it is held with an insulating handle. It will become charged only if it is held with an insulating handle. Otherwise, the electrons are transferred between the conductor and the ground via the person's body. So it cannot hold like this. An insulator can hold this kind of charge, but in a conductor, if that conductor is held with some insulating handle, then that electron may be carried. Otherwise, that electron can be transferred between the conductor and ground by the human body or the person's body. So this is the main difference of electrical conductors and insulator in terms of electron. Explain what you mean by an electric field. When an electric charge is placed near another electric charge. Suppose if one electric charge is placed and some other electric charge brought near to it, it experiences a force. So one charge has an electric field in its surrounding. If another charge comes, that charge will experience a force on that charge, on the other charge. So the electric force does not require contact between the two charges, so we call it an action at a distance force. It acts across space. So action at a distance force. So the region of space where an electric charge experiences a force due to other charges is called an electric field. So the part B, sketch the electric field lines including their direction between two oppositely charged conducting parallel plates, indicating the direction in which a positively charged would move if placed between the plates. So this is two plates, a positive charge plate, and this is a negatively charged plate. So if the electric field felt by a charge in the same everywhere in the region, so this kind of parallel conducting plates, so the field is uniform. The field is uniform everywhere. Your uniform electric field is produced between two oppositely charged parallel plates, metal plates, as shown in figure this. It can be represented by evenly spaced parallel lines drawn perpendicular to the metal surface, like this. The direction of electric field at a point, for example this point, is denoted by an arrow, is the direction of the force on a small positive charge placed in the field. Negative charges experience the force in the opposite direction to the field. Positive charge experience in one direction and the negative in the other direction. Electric field is a vector quantity as it has both magnitude and direction. So this is direction and magnitude, the strength. If we brought this bar is closer and then more experience, it will experience more force. So magnitude and direction is there. The unit of charge is always in coulombs. Charge is always defined in coulombs. So state the direction of electric field. The direction of electric field at a point denoted by an arrow in the direction of the force on a small positive charge placed in the field. Negatively charged experience a force in the opposite direction to the field, as shown in this figure. Electric field is a vector quantity. It has both magnitude and direction. Draw the field lines around a positively charged conducting sphere. So the electric field lines radiating from an isolated positively charged conducting sphere. For this is a positively charged sphere, and a point charge are shown in figure 4.27 AB. This is a point charge, and this is a spherical charge body conducting, shown A and B. The field lines again emerge at right angles to the conducting surface, like this. So the field lines always emerge perpendicular to the surface. So this is the tangent and this is always perpendicular. Here this is a tangent to the surface and this is perpendicular. Here this is a tangent line and this is perpendicular. So this we can understand this. So this is all from this. Suppose study the circuit in figure 4.234. The switch S is open. This is open in every circuit. There is a break in the circuit at this point. In which circuit would lamp Q and R light but not lamp P? Q and R. So we have to glow Q and R but not P. So in this circuit, Q and R will glow but not P. Is B circuit. So whenever we switch this, so this is short. Whenever we switch this, switch is open, the break at the circuit. In which circuit? Okay, this if it is open, circuit, the switch is open, there is a break in the circuit at this point. In which circuit would lamp Q and R light glow but not lamp? So this circuit is this switch is open everywhere, so this circuit is incomplete. Similarly for this if this is open, then Q and R, this is, and the continuity is not there. Similarly for this, if this is open, then there is no continuity. For electric flow, the continuity should be there. For this open, this continuity is already exist, so this will glow. So this B circuit is correct. That's why B is the answer. Using the circuit in figure 4.235, which of the following statement is correct? When S1 and S2 are closed, S1 and S2 are closed, lamp A and B are lit. When we close, then this becomes a short circuit and this will not glow. Only B will glow. When S open, S is open and S2 close, no one will glow because this circuit will not complete because this is terminating here. And with C, S2 open, if this is open and S1 is closed, then A, B are lit. Yes, this is positive, it will flow like this. So this is a battery, and if this is closed, the path will be completed from positive to negative. For conventional current and for otherwise for electron, it will also work. But this, if this is open, then both lights will glow. So C is correct. Identify the particle which carry a current in a metal. Free electron. The free electrons is the particle which is used to current in the metal. Explain difference between direct current and an alternating current. The direct and alternating current difference is there. So in a direct current, the electron flow in only one direction. In a direct current, the electron flows in only one direction. Graph of steady and varying DCs are shown. So the net effect is always positive. Here this is, if you take the average, the result will be a positive like this. So average value will be somewhere here. So this is also a DC, but here some values are varying, but in a limited band. So the net positive effect is positive. In alternating current, the direction of the current reverses regularly like this. So here in this positive cycle and negative cycle, the same. The average value will always be 0. The direction of the flow reverse regularly as shown in the graph in figure. The graph and the circuit sign of AC is given in figure 4.216. This is the symbol of this AC. Explain where you would connect and how you would use an ammeter to measure the DC current in a circuit. So ammeters are always used in series. Ammeter is used to measure current. It should always be placed in series in a circuit. In series in a circuit with the positive terminal on the ammeter connected to the positive terminal of the supply as described in the practical workbook. See figure 4.213 below. A simple magnetic moving coil ammeter will read DC current only on an analog display. It may have 2 ranges and 2 scales in the display like this. So we have this measuring current. So this is ammeter and this is load, a glowing light, a bulb, and this positive is connected to this positive and will work like this. Connect circuit is this unit on a circuit board if possible. Ensure the positive of the cell metal stud goes to the positive of the ammeter marked red. Note the current. So this is the way the ammeters are connected. Define electric current. Electric current is defined as the charge passing through a point per unit time. Charge passing through a point, passing through a point per unit time, and can be written in a symbol as this: I is equal to Q upon T. I is the current where charge Q passes any point in the circuit at time T. So if the charge passes through any particular point for time T, then this mesh current has flown through any of the circuit. So it shows that the current is the rate of flow of charge. So current is basically the rate of flow of charge. It's a flow of charge. This is a charge, and with reference to time, so it's a flow of charge. So current is the flow of charge in a particular time. So it shows that the current is the rate of flow of charge. Rate of flow means with reference to time. Rate means of charge flow with reference to time. In a circuit, the unit of time current is amperes, and 1 milliampere is the 1,000th of this ampere, the very small quantity milliampere. And for larger quantity, the ampere is a bigger quantity measuring unit, and the milliampere is a smaller measuring unit. It is 1,000th of this ampere, is 1 milliampere. Electric current passes through a device. Current is measured by an ammeter. Calculate a current at a point in the circuit where the 180 coulombs of charge passing in 1 minute. 180 coulombs of charge passing in 1 minute. So I is equal to Q is equal to 180 C, and T is equal to 1 minute. So this is 60 seconds. So I is equal to Q upon T. The 180 divided by 60, 3 coulombs per second. So that is 3 ampere. If the current in the device is 2 ampere, so current is 2 ampere, what charge passes through in 1 minute? So time is 1 minute 60 seconds, so we have to find the charge. So Q is equal to IT, so I is 2 ampere, and this T is 60 seconds, so this is 120 coulombs. Charge will be passed for 2 amperes for 1 minute. So if the current in a flood lamp is 5 ampere, what charges passes in 10 seconds? So I is equal to 5 ampere and time is 10 seconds, then Q is equal to IT. 5 ampere 10 seconds is 50 coulombs. For 5 minutes will be much larger, so 5 minutes, so we'll multiply it by 5 into 63, 30, so it can easily be obtained. So this is 5 minutes, and this is IT, so this is 1500 coulomb. The lamp and the cell in all of the circuit of the figure 4.236 are the same. If the lamp in A has its full normal brightness, what can you say about the brightness of the lamp in B, C, D and F? So here we have single voltage, here we have double and double load, here we have double circuit and double. Here the connection is different. So this is negative and this is positive, positive, and this is positive, negative, positive, negative, positive, negative. So 3 times. This is also different. This is opposite. So everyone has its different combination. So let's discuss A, the full and normal brightness given, because P is equal to VI. For B, P is equal to 2V into I, because for this B circuit the voltage is double. This is 1V and 2V, so the voltage is double, so this is double, so the power is double. Since power is double, brightness will be double. In C, the voltage drop in each lamp is equal to V, is V. So 2VI, V upon R, so this is 2VR. Brightness will be same because there are 2 lamps are there. So this V square upon R will be same this for this one. So because this is V upon R, so V square upon R for the one lamp. So here we have 2 lamps, so one lamp will have V square upon R, the second lamp have V square upon R, so 2V square upon R. So both lamp will have the same glow like lamp 1 A. These both lamp will have the same glow like A. In part C, same as C, and say E. This is 3 voltage, and here we have this, so the voltage is 3 times, so the glow will be more. So 3 times this, so this is 2.5 times of this glow, so the brightness will be more than double, because this is 3V and this is I is 3V upon 2R. So this is 9 times upon 2 V square R. So the every lamp will glow 2.25 times. So the brightness will be more. For F part, the brightness will be 9 times because this is 3V is applied here. 3 volt is applied here. But this connection is wrong. So if we have this one positive here and this, so this will cancel each other. So if we assume that this is in a correct combination, this, if this is positive and this is negative, then this is 9 times. Otherwise it will be less. So because this 2 will cancel each other, so this 2 will cancel each other, and then this brightness will be same like this for this connection. So I've assumed this line is bigger line is here, a smaller is here, so all is in series. So this is not the case in F. Sorry, for E. This is not correct for this one, because if F is like this, then this will be the brightness. If this is a positive terminal, this is negative. Here this is positive and this one is negative. So this we have only V voltage applied, because this will cancel each other and this only this voltage will be applied. So it will be like this, like this. So if we have this all positive in a series, but this is not, because this is cancelling each other, so this will not be the answer. F part is not correct. If we change this terminal, interchange this positive terminal here and negative here, then the answer is will be this. It's 9 times higher. So the 3 voltmeter V1, V2 and V1 and V2 are connected in, as shown in figure 4.237, like this. So this is voltmeter 1, 2, and this is voltmeter here. So this is ammeter. If V reads 18 volt and V1 reads 12 volt, if this V reads, this is reading 18 volts and this is reading 12 volts. So this is two lamps are in series. This is, so the voltage across these two lamps is 18 volts. If this is 12 volts, then the voltage across this lamp is basically 18 minus 12, which is 6 volt. So V is equal to 18, V1 is equal to V2 is equal to V minus V1 is equal to 18 minus 12 is equal to 6 volt. If the emitter reads 0.5 ampere, how much electrical energy is changed to heat and light in lamp L1 in 1 minute? So current, this circuit is in series. Both loads, these are the loads, lamp are the loads, and the current flow through this way, and the same current will flow from lamp 1 and lamp 2. So if the current is flowing, reading is 0.5 ampere, means every lamp is passing through 0.5 ampere, and so energy is equal to V into I into T, and the voltage across this lamp, we have to find L1, sorry, this one. So this is 12 volt, so this is 12 volt, and current is 0.5 ampere, and the time is 1 minute, so that is 60 seconds. So 60 seconds, so 12 volt, 0.5 ampere, and 60 seconds is 360 joules. So 360 joules energy will be utilized here, because this is 12 volt, this is 0.5 ampere for 1 minute. So we'll use it. Copy figure 4.237 and mark a positive terminal of the ammeter and voltmeter for correct connection. To mark positive on the A and V. this is positive here because it is connected to this positive terminal. So positive terminal should be marked here. Similarly, this is positive and this is negative. Positive and negative. Voltmeter terminals. Similarly, positive and negative. So graph of figure 4.237 illustrate how the potential difference across the end of conductor is related to the current in it. So this is potential difference and this is current. So state the relationship between voltage and current that can be deduced from the graph giving the reason. Figure 4.38 is basically the V upon I. So we divide the voltage by the current. So this is voltage and this is current, potential difference. So divide the potential difference by the current, we get the resistance that is constant because it's a linear relation, very close to the straight line. So this is a practical value. So this is almost a linear relation. Describe how the resistance of a wire depends on its length and cross-sectional area. So resistance is directly proportional to the length of the wire and inversely proportional to its cross-sectional area. So this is the relation of the resistance with the wire length and its cross-sectional area. The resistance of a wire of a length 1 meter is 70 ohms. Calculate the resistance of 20 centimeter length of wire. So 1 meter length is 70 ohms. So L2 is 20 centimeter, that is 0.2 meters. So R2 is equal to L2 upon L1 R1. So this is relationship. R2 upon L2 is equal to R1 upon L1. So this is 0.2. This is 1 meter. This is 1 meter, 0.2 meters, 1 meters, and this is R1 is 70 ohms. So this is 70 ohms. We just plug in the values here. This is L2 is 0.2 ampere, 0.2 meter, and L1 is 1 meter. So this meter will cancel, and this 70 multiplied with this. So this is 14 ohms. So length is 5 times lesser. The resistance will be 5 times lesser. If you multiply with this 5, you will get this 70. So if length is 1/5, this 20 centimeters is a 1/5 of this 1 meter. So the resistance will be 1/5. Very easy. If 1 meter of length of wire is replaced with a wire of same material and length but of half of the diameter, calculates its resistance. So the resistance is 70 ohms. Dia D1 is D and the second dia is 2D. So if we change the dia, then that value will be changed. So area of cross-sectional area is pi by 4 D1 square. This A2 is pi by 2 D2 square. And by changing the dia, we will have, so if the length of wire is replaced by a length of half of the dia, it calculates its and the length of half of the diameter. If we double the diameter cross-sectional, then its resistance will decrease. If we reduce the dia, half the dia, then its resistance will be 4 times increase. So this is, if we increase the cross-sectional area double, then its resistance will be decreased 4 times. If we reduce half the dia, then its resistance will increase to 4 times. Here we have include the dia as a double the dia. So initial the dia is D and we have increased the dia. So if we increase the dia, double the dia, then means cross-sectional area is increasing. Cross-sectional area increasing means resistance will decrease. So resistance will decrease to 17.5. If we increase the dia, if we reduce it to the D by 2, rather than 2d, d by 2, then in placing d by 2, then it will be d square, d square, and 4 times will be here. So this 4 into R1, which will be this 280 ohms. So for this case, we have assumed this, so that's why we have obtained this result. If you multiply with the 4, we will get this 70. Sketch the current and voltage graph of the resistor of constant resistance. So this is already shown in figures like this. This is ohmic resistance, this is semiconductor diodes, this is filament lamp, this is thermistor. This filament lamp is when it gets hotter, it gives a non-linear relationship. This is semiconductor diode, and this always conduct in one direction. In the other direction, it isolates. It does not allow conduction. Only thermistors have this kind of behavior. From this part, we will discuss in the next session.